Hello again, let's look at some examples. If f of x equals absolute value of x for all real x, and if g is a function from the reals to the reals such that g of 7 equals 1, whereas g of x equals this difference quotient, which is this guy right here, for any x other than 7, then the limit as x goes to 7 of g of x, but hey, that's going to be the derivative of f at x equals 7. Because that's going to be the limit as x goes to 7 of this guy right here, f of x minus f of 7 over x minus 7. I go ahead and allude to that right here. I kind of put this in front, but it's okay. It might have been more clear if I'd put it over here, but anyway. So that is going to be f prime of 7, so that's that limit. But now, guys, as x gets indefinitely close to 7, very, very close to 7 without hitting it, you know, it's going to be at either like 6.99999 something something or 7.00001 something something. But anyway, or something akin to that. It's going to be, point is, it's going to be very close to 7, so it's going to be nowhere near x equals 0. So the absolute value of x will safely equal x. We can safely say that because x is arbitrarily the limit. X is moving towards 7. So absolute x equals x. We can, because we're in the positive domain realm, as x zones in on positive 7. Now, absolute 7 is, of course, 7. So we just get, hey, we get x minus 7 over itself. That's just 1, and we know that the limit x goes to 7 of 1 is 1. So f prime of 7 equals 1. And you know what? 7's not sacred at all. I could replace 7 with any positive number. So for for a positive number c, absolute x minus absolute value of that positive number c over x minus that positive number c equals limit, and then again for the same reason we're just going to get x here. That's the important part. X minus positive c over x minus positive c, and we just get 1. Now, if c is negative, life is almost as easy, but a little bit of care has to be taken. We'll just go down here, and this will take care of that. If f of x equals absolute x again for all x, and if g is a function, and my ability to spell went away from me on that one. So if g is a function, now we're going to define g a little bit differently. It's going to be f of x minus f of negative 7 over x minus a negative 7, which is x plus 7. I just went ahead and abbreviated that down here. Hey, this is just the difference quotient relative to negative 7. This guy up here was the difference quotient relative to positive 7 that we did a minute ago. So now we're dealing with negative 7. The limit as x goes to negative 7 of g of x is f prime of negative 7, and which is going to be absolute x minus absolute negative 7 over x minus negative 7, and that's where the x plus 7 comes from. But now be careful about something. As x zones in arbitrarily close on either side of negative 7, it's not going to be positive. It's going to be negative. So the absolute value of x is going to equal negative x, not just x. Because think about it. Like the absolute value of negative 12 would be the negative of negative 12. So that's why you need the negative x. And I'm just using negative 12 as just an example of the absolute value. It has nothing to do with the problem at hand. But anyway, coming back, so we illustrated absolute value of x equals negative x. Or I motivated, I should say. And then minus, the outside minus sign isn't going to be affected. Now the absolute value of negative 7 is just 7. So this negative right here gets killed by the absolute value. But not this one here, however. But hey, negative x minus 7, you can take out a negative sign, which is an understood negative 1 out here, and you get negative 1 times parentheses x plus 7 over itself, x plus 7. That just leaves negative 1 behind, and you just get negative 1. So the derivative of f at negative 7 is negative 1, and for that matter, the derivative of f at any negative number is negative 1. You remember, for any positive number, it was positive 1. For any negative number, it's negative 1. As 0 itself, it's going to turn out that it does not exist. You don't have a derivative. It's undifferentiable at x equals 0. So, and I allude to that down here. I don't know if I worded it in the best possible way. So here's our f again. If Oops, and I really should say f of x. So if f of x equals absolute x for all real x, and if g is a function, again, from the reals to the reals, such that g of 0 is 0. Now this time I'm going to let g of 0 equal whatever. It's not going to matter. G is going to be discontinuous at 0. You know, I may as well, in a way, I could have just as well left g undefined at 0. It's not because nothing I do here is going to save continuity. I can save continuity from one side, but I can't save it from both sides. And here's why. Now, I'm going to go and define g of x to be absolute x minus... Well, hey, this is really just absolute x over x right here, okay? But anyway, so we get absolute x over x. Now, if you come in from the right, absolute x is just x. So, and we get x over x, and we get 1. However, the trouble is with 0... The trouble with 0 is you're always indefinitely close to a negative and a positive number at the same time. You don't escape from either one. The limit as x goes to 0 from the left on the negative side, absolute x is negative x, not just x. And you get negative 1. The one-sided limits do agree. They don't agree. They do exist, but they don't agree. And the fact that they do not agree means that the overall limit as the ordinary limit as x goes to 0 of absolute x over x does not exist. G is discontinuous at 0, and that means, and notice that this is f of x minus f of 0 over x minus 0, and this is the one-sided limit, and this is the other one-sided limit. They don't agree, so f is not differentiable at 0 because the ordinary limit as x goes to 0 of f of x minus f of 0 over x minus 0, that overall limit does not exist, so f is not differentiable at 0. Oh, now the absolute value, f is continuous at 0, but it's not differentiable there. So we have found a function that is, notice that if x equals 0, f of 0 is 0, so graphically this is at the origin. You know, on the graph, the absolute value function, just the ordinary absolute value function without any shifting or anything like that, the origin is one of the points. Now, it's continuous at the origin, meaning you don't have any jumps or empty holes or infinities. That's good, but it's not differentiable there. What's happening is at the origin, you have what's called a sharp point. Like, follow my cursor just for a second. You do this, then you hit the origin, and then you turn around and go back up here. So you're kind of coming in from, you're going down right at a 45-degree angle relative to the negative x-axis. Then you hit the origin, and then you kink up, so to speak, and now you're going at a 45-degree angle relative to the positive x-axis. So you go, you do this, then you do this, okay? You get an hourglass. If you have a sharp point, that is always indicative that you're not differentiable at that point. I think I can safely say that. On a graph, if a point is a sharp point, even if you're still continuous there, if it's a sharp point, differentiability is lost. Now, if you're discontinuous, of course differentiability is lost. You have to be continuous to even have a chance of being differentiable, but just because you're continuous, that doesn't promise that you'll be differentiable. Now, if you're differentiable, you will be continuous, but just because you're continuous at a point, that doesn't necessarily mean that you're always going to be differentiable at that point. A lot of times you will be, but you won't always be. Like in this example, back at 7 and negative 7, we had everything nice. We were differentiable, and from that we could conclude that we were continuous. At 7 and neg 7 and for that matter, any positive or negative number, likewise, we're differentiable and everything nice. But at 0, we're continuous. We're only continuous without being differentiable at 0. So at 0, we don't get everything that we want. So this function is not differentiable at the origin, namely the absolute value function, even though it is continuous at the origin. Now it's differentiable everywhere else. At x equals a positive number, the derivative is 1. At x equals a negative number, the derivative is negative 1. But at 0, the derivative does not exist. That'll be all for this video. I think that's enough. I'll see you on the next video.